We are here to talk about determinants, determinants from the ground up. So, two pieces of paper here with words and pictures. And let's go through kind of an idea here for the 2x2 determinant. So, lots of ways that people approach determinants. We're going to frame it around area. And the area in particular that we'll look at is the area of the parallelogram generated by the two row vectors in this 2x2. We've connected at other times what the determinant means in terms of null spaces and all sorts of things. So, but now we're just going to calculate this kind of single number that every n by n matrix has, and we're calling it a determinant. So let's just approach it in this way. All right. So here's AB, the vector AB. Right, so we'll use red for the first row in general, and CD is here. So we'll use blue for the second vector. And so we'll have a number of examples, as you can see here. Right, so here's our first one. We're going to stack it up here as well, and then put the second row here. So this is obviously very general. This is just a general version. And we want to figure out what the area is in here, and we're just going to say this is the determinant. All right, so and you can see when these things are going to be parallel, this will squeeze up and there'll be no area. So that's an important thing. And that corresponds to when we have a matrix that's not invertible, that has a non-trivial null space, all sorts of goodness. All right. Okay, but let's do this. All right, so the length of this big rectangle here is A plus C. All right, so that's the two x1 components. And then B plus D up here. So that's going to be the area of, so the area of our parallelogram will be that area of the whole thing minus these pieces here. So, and I've drawn them out here. So these two triangles match up with each other. Length A and height B. So we can just join them up to make a rectangle. So it's minus A times B. There's a minus D times C here for the ones shaded with gray vertical lines. And then there are these two rectangles here, and they have length C and height, width C and height B. So minus 2BC. So we can expand this, just a tiny bit of algebra, right? So we get an AB and an AD, a CB, and a CD. That's expanding this. And then they, various things cancel out, so the ABs go away. CBs go away, this CB goes away, and we're just left with minus BC. This CD and this CD disappear. So we're left with AD minus BC. And we'll call this A for 2x2. This is determinant, and we write it as determinant of A with brackets like this, DET, or use this a lot, just straight lines around A. And so that's here as well. Just straight lines. So it's a bit subtle. Of course, we use square brackets to indicate a matrix. This is a box, 2x2, right? There are 4 numbers in here. This is just one number, right? It's a scalar quantity associated with this matrix. So when we put lines around it, we mean figure out the determinant. That's what it is. All right. So that's AD minus BC. That's our little formula now. And so we're going to make 3 observations about it. They're somewhat out of order. So let's go to the right order. So for the identity matrix, 1, 0, 0, 1, right, our excellent identity matrix, we'll use this as an anchor. The determinant is 1, right, follows from our little formula. There's 1 times 1 minus 0 times 0. And it makes it so it's clear from this picture. So again, the first vector is here, 1, 0. The second one is blue, red, then blue. Yeah, the area of this is 1. And so we can see how this will generalize to an n by n. So we'll have a hypercube with volume 1. All right, so that's going to be our sort of starting point. And in fact, it's the only area we have to calculate. We can express the area of this one in terms of the area of this. All right, so that's very simple. The second one is a subtle kind of weird thing, which is if we swap the rows. So if instead we had CD, A, B, so we took our matrix, we swapped its rows, then and use our formula again. So our formula is B, it'll now be these two multiply BC minus AD, and that's the negative of the original determinant, right? So if we swap rows, we change the sign of the determinant. We still get the same value, but same magnitude, but we change it. So we'll generalize that for n by n's to say if we swap any two rows. So this is just an observation here. We're going to sort of leap a little bit there. But one way to think about this is, here's our first vector, our second vector. We're moving in a nice direction here. Right? This is the way we usually define things. This is moving in a positive direction. If we swap them, then we'd have to move back this way. And obviously something happens when we get to 180 degrees. But that's the idea. It's sort of a handedness of the system that you're creating with these vectors. Okay, all right. So that's a peculiar thing. And then multilinearity. So in the rows of A. So linearity you know about. Multilinear means that it's determines a linear row by row. So from an area point of view, this should make sense. So if we triple the first row, and again, this is a determinant, we're just calculating a determinant, then this is the same as, so if we take the determinant of the matrix A, but we've got 3 times the first row instead, then that's the same as multiplying the determinant of A with 3. All right, and here's the picture of it. We've stretched the parallelogram in one direction by a factor of 3. Right, so there are 3 of these areas in there. Because it's an area, we don't pull this out and get 3 squared. And if we had a 3 here and a 3 here, we would get 3 squared, right? So if we'd stretched it 3 times in this direction, 3 times this direction, that would turn out to be a 9. We're multiplying the area by 9. And so here's another example. We've doubled it in the AB direction, and we've multiplied by 4 in the CD direction, and that leads to increasing the area by a factor of 8. So that's an important feature. Now, so that's a part of the linearity. The second part is a bit odder perhaps, but it's that we can actually add determinants together if we're adding one row at a time. So here's an example. It's a matrix we'll look at a little more. So it's 2, 3, 1, 4. We can split it in this way. So this first row vector and this first row vector add up to give you this one. And we're not changing the second. So it's in keeping with this here, where this 3 comes out of here. We didn't change the CD. So this doesn't work if this is actually a normal matrix, right? If we had square brackets here and we're talking about normal matrices, that doesn't work. Well, you can't just pull 3 out of it. So this is a sort of a strange kind of departure from that. But we are not talking about numbers in boxes anymore. We're just talking about this whole thing is one number. And from our formula, the number here is 8. 8 minus 3, which is 5. So here it is. Right, 2 times 4 minus 3 is 5. So let's go over to the next one. 2 times 4 minus 1 times 0. So it's 8. 0 times 4 minus 3 times 1 minus 3. Cool. And so 5 equals 8 minus 3. So that works, and this minus sign matters. And in pictures, let's look at it. Here's our the matrix we started with, 2, 3, 1, 4. So here's the 2, 3, it's in red. Here's the 1, 4. We make a little parallelogram. That's area 5. And these simpler, so you can see these are simpler. Why we've chosen 2, 0 and 0, 0, 3 is important. We'll come back to that. These are simpler looking parallelograms because now one side is lined up with the coordinate system. In both of them, here it's the x1 direction, here it's the x2 direction. And so we can see, yeah, so this is an area 8 here. It's more than this area. Not necessarily drawn that well. And what's happened is, here's the first vector, here's the second row vector, right? So here's 2, 0, here's 1, 4. And now this is 0, 3, and this is 1, 4. So you can see that the order of these things swapped, right? So from the first vector, we have to rotate what's in the negative direction to get to the blue vector. So this ends up being a negative quantity, right? The area in here is 3, but we get a sign which refers to how we laid out the vectors that define it, define that parallelogram. Here's another example. So 2, 3, 1, 4 again, and we've left the top row the same, right? and split up the bottom row. So splitting up the bottom row, just arbitrarily, this is just an example. So minus 7 plus 8 is 1. 8 minus 4 is 4. So there's a linear piece here. These two rows add. And that's why it's, again, multilinear. It's row by row. And let's figure it out using our formula. So 2 times 8, 16. You always get a little tripped up with this. It's minus 3 times minus 7. So that's plus 21. So 37. And then minus 8 and minus 16. Minus 24. So it's minus 32. So 37 minus 32 equals 5. So that's good. All right. So this is, we've defined this one number based on for a matrix, this determinant, and the intuition is this geometric one, right? So it's an area associated for 2x2s with a parallelogram. For 3x3s, it becomes a parallelepiped, and I may have to say that. Yeah. So, right. So now we sort of branch out. So this is what we're going to talk about n by n's, and we'll assert these three properties, right, for n by n matrices. So again, as we had very simply for the 2x2, the volume of the unit hypercube is, let's write that, n by n is 1. We'll set that. Swapping any two rows again changes the sign of the determinant. And then determinants are multilinear in their rows, right? And let's add this. The determinant equals plus or minus the volume of the parallelepiped, which is hilarious. Parallelepiped, created by the row vectors of A. All right. Yeah, so for the identity matrix, we have 1, where it's all very simple. Unit vectors along all the axes, so it makes a little hypercube. But in general, it's going to be this funny looking high dimensional parallelogram thing. Okay. So we've noticed this about this. We've noticed these three properties, and we're going to then assert them. And the idea is we can connect any determinant to the determinant of the identity by doing these things, right? We can use multilinearity and then row exchanges to move from A to the identity. And so we'll just do a simple example here. The next part will be getting back to our standard row operations and showing how we can use all of those in a good way. So let's just kind of go through this process, and there's some guidelines as to how we move, but 2, 3, 1, 4. So we just did split this up, and there was a reason for splitting it into 2, 0, and 0, 3. But rather than minus 7, 8, 8, and minus 4, these are still complicated parallelograms. Complicated in the sense that they're not lined up with the axes. These ones are much simpler, and you can see maybe we can then move this one across and then bring this one down, so you can see that that's going to be a simpler thing to do. So that's why we've introduced these zeros here. Right? First, these top rows add to give us 2, 3. So the zeros were an important thing. The bottom rows are the same. So it's linearity. So we're using this property here, property 3. It's linear in row 1. So then we can do that again. Now we'll use linearity in row 2. So again, this is property 3. So 2, 0, 1, 4. We're going to split up. We're going to introduce zeros again. So 2, 0, we can make it 0, 4, and 1, 0. Right? So these bottom rows add to give us 1, 4. 2 zeros on top, unchanged. 0, 3 is on top, unchanged. And then we want 1, 0, 0, 4. Okay, yep. And this one, we're very close. So the parallelogram here, it's a 2, 0. So again, red one first. And then a 0, 4 here. So this is easy. We can see what this one is. It's area 8. There's one more step we'll do with that. This one is, so it's beginning to look like the identity matrix, but the rows need to be swapped, so we'll do that soon. So 0, 3 here, and have I drawn that? And then 1, 0. It's not the right thing. So this should be, yeah. So we really wanted 0, 3. So that's up here. Okay, good. Let's draw it like that. And then, sorry, it's confusing myself. So red for the first one. And then blue for the second one. I believe that's what I've done. This one is out. And so this is this guy. Okay, off you go. This is, yeah, so 0, 1. Sorry, 1, 0. And, yep. 1, 0, and 0, 3 here. Good. All right. And so you can see the area of this will be 3. It's not hard to see, but still we want to make it, this still doesn't look like the identity matrix, so we're going to pretend we don't know what's going on yet. So these other ones have, we've introduced zeros in their columns, right? So I have 2 columns that are all zeros. And we can use this next step of multilinearity, which is about the scaling. So we can pull a 2 out of the first row and a 4 out of the first row. So it's 2 times 4 times what's left, which is the identity. We can pull a 3 out of this one, so it's 3 and then 0, 1, 0. And we'll clean these up as well. So we'll pull a 2 out here and a 3 and a 4 out here, 0, 1, 0, 1. And then let's look at their parallelogram. So both of them are pointing in the same direction, so 1, 0, 1, 0. So there's, I suppose I've taken the scalings out, so this should be exactly the same. Good. Right, so the volume of these is 0, right? We're still thinking about volume. Okay, good. So these disappear, and we'll be able to say things more generally about this. This kind of form, 0, 1, 1, 0. Okay, so that's almost the identity matrix, and now we're going to finally use 2 for the first time. So we'll swap these rows and introduce as a -1. So we have 8 times the determinant of the identity, -3 times the determinant of the identity. So 8 minus 3 times this, and this is, of course, 1. All right, so 5. So that's the idea. We moved it all the way down to, and we could just leave it as this, 5 times the identity's determinant, which is 5. Right. But the game was to connect the determinant of A all the way down to the determinant of the identity. All right. So the next business will be to bring in our row operations. We'll just use them, and we have a very structured way of doing them that will help us once again. So a bunch of results turn up. So one is that, again, this is for n by n's. Determinant of A is plus or minus the determinant of U from LU decomposition, right? So this is from PA equals LU. I know you're excited about that. And then, so this is, it's not obvious this will be true, but the determinant of A times the determinant of B is, the determinant of AB is the determinant of A times the determinant of B. You can't do anything for adding, so determinant of A plus B, that doesn't work out, but this turns out to be true. So that's a good thing to think about. And this is a carrot. It's going to go into some soup. Thank you.